This topic is about determining the points of discontinuity from a graph. So before we start this problem, we need to understand what is continuity, what does it mean to be continuous, and then what does it mean to be discontinuous. So let's go into those definitions now. Okay. It says, in the previous section, we discovered that to evaluate the limit of a function at a point, sometimes we can simply plug that value into the function directly, while other times we cannot. Then this naturally raises the question, when can we evaluate the limits by direct substitution? So again, in the last section, what we found out was the first thing you always try doing when evaluating a limit algebraically is plugging in the number. If it works, that's great. That is your limit value if you get a number out. If you get something like 0 over 0, that was an indeterminate form, and you had to do things like factor and simplify, multiplying by the conjugate and then simplifying. So you had to use different techniques when it wasn't defined at that point and to try to figure out the limit, which was a huge pain. So when do we have those nice functions? How can we know we have those nice functions when we can just plug in the number directly? So the answer lies in the idea of continuity. When a function is continuous at a point, the limit as x approaches that point is equal to the function's value, and direct substitution works. So if a function is continuous at a point, that means to find the limit, just plug the number in and you're going to get the answer. So it's really important to know when is a function continuous and when is it not continuous. And when it's not continuous, we call it discontinuous. So what does it mean to be continuous? Here's the definition of continuity at a point. A function f of x is continuous at x equals a if all three of the following conditions are satisfied. First, the function value has to exist. So when you plug in x equals a, it has to be defined. You do have to be defined at that point. No open circles, no division by zeros, no square roots of negatives. Okay. The limit also has to exist. And remember, for the limit to exist, the limit as x approaches a from the left has to equal the limit as x approaches a for the right. So you couldn't have any jumps where the limit from the left and the right did not agree. And the last thing is that the limit equals the function value. So whatever you found in part 1 and whatever you found in part 2, the function value and the limit, they have to agree. And if you meet all three of those conditions, you are continuous at that point. But if any one of those three conditions fail, it is not continuous at x equals a. So when it's not continuous, that's called discontinuous. So anytime you're going to tell me that a function is discontinuous at a point, you are going to reference one of these three reasons as to why it is discontinuous. You are either going to tell me the function doesn't exist at that point, you're going to tell me that the limit doesn't exist at that point, or you're going to tell me, hey, they both exist, but they're not equal. Okay? When a function is continuous at every point on an interval, we say that it is continuous on that interval. So how do you determine the points of discontinuity from a graph? It says continuity can be understood visually by looking at the graph of a function. When we analyze a graph, we check whether the function meets the three conditions for continuity at a point. To determine whether a function is continuous at x equals a from the graph, first we want to check to see if the function value exists. Look to see if there's a solid point on the graph at x equals a. If there is a hole, an open circle, or the function is not defined at a, then f of a does not exist and the function is not continuous. So you would say the function doesn't exist at the point, so it's discontinuous there. The second thing you need to do is check that the limit exists. And remember, this is where we had to trace the graph from the left side and the right side as x approaches that given value. If both sides approach the same function value or y value, then the limit exists. But if the left side and the right side approach different values, or if the function goes up to infinity or down to negative infinity, growing without bound or decreasing without bound, then the limit does not exist. Check that the limit equals the function value. So if they both exist, you need to make sure that they're equal. So it says confirm that the y value that the graph approaches as x gets closer to a, which is the limit, is the same as the solid point at x equals a. If they are equal, the function is continuous at x equals a. If the point is missing in the wrong place or it does not match the approaching value, then the function is not continuous at x equals a. So what are common graphical clues of discontinuity? What does it look like at a point of discontinuity? Well, first of all, maybe it helps to say, what does it look like at a point where it is continuous? If you want to graph and see when a graph is continuous, what you're looking at is, can I graph the entire thing without lifting my pencil? If you can graph the function without lifting your pencil, then the function exists everywhere, the limit exists everywhere, and they're the same thing, therefore it is continuous. So essentially, it's anywhere you have to lift your pencil. If you were drawing the graph, that would be a point of discontinuity. What do those look like? Well, first of all, you could be dealing with a hole, which is called a removable discontinuity. So this is where my limit exists, but the function's either undefined or defined at a different value. So here's two examples of holes in the graph. This first one has a hole in the graph where the function's not defined, and it's not defined above it, below it, it's not defined anywhere. So this is just straight up a hole. So notice here that f of 1 does not exist. Since the function doesn't exist, the limit is not continuous. On this next one, notice we have this open circle here, but a closed circle here. So you would say that f of negative 1 in this case actually does exist. It's defined right here at a point. Notice also that the limit from the left and the limit from the right is 2, so the limit exists on this function as well. So what's the problem here? This one is the problem where the limit exists, the function exists, but they're not the same thing. So let me write these down for you here. This first one was where the function does not exist. The second one, the function exists and the limit existed, but they were not the same thing. So on this one, you would say that f of a is not equal to the limit as x approaches a of f of x. So that violates the third condition. The next one is a jump. And the jump is when the left and the right limits approach different values. So notice on this one, from the left, it looks like I have a y value of 0. From the right, it looks like I'm approaching a y value of negative 2. And from the left and from the right, those aren't the same values. If those aren't the same values, we have that jump in there. We know that the limit does not exist. And if the limit does not exist as x approaches a, then the function is not continuous at that point. The last case that we look at so again, we have the two cases of holes. We have a case of a jump. The last one that we'll see is vertical asymptotes. Notice from the left it goes down to negative infinity, and from the right it goes down to infinity. This one, the actual function is defined. I do see a closed point here. So the function is defined here, but when you go down to infinity or up to infinity, your function does. Technically, your limit does not exist. And if the limit does not exist, because, by the way, a limit has to equal a number. You can't ever equal infinity or negative infinity. Those aren't defined. So technically, the limit does not exist. So that would be the reason. Limit as x approaches a of f of x does not exist. Anytime you see a vertical asymptote, the limit doesn't exist, so the function's not continuous. So there you can see all three violations of the case. Here's one where the function didn't exist. Here's a couple examples where the limit didn't exist. And here's an example where both the limit and the function exist, but the problem is they're not the same. And those were the three conditions that we had to meet to be continuous. Function exists, limit exists, and they have to be the same. So, in short, look for holes, look for jumps, look for vertical asymptotes. So the question says, the function g is graphed below. At what numbers in the interval negative 4 to 4 is g discontinuous? So we're going to look anywhere the function is discontinuous, where it has a hole, where it has a jump, where it has a vertical asymptote. There are no vertical asymptotes here, but I definitely do see some values like this one right here. That's a hole where it's defined somewhere else. This one right here, that's a hole. It's not defined somewhere else. This one right here, when x equals 3, looks to me like we have a jump in the graph right there. So those are the three places that I'm looking for discontinuities. When x equals negative 1, when x equals 1, and when x equals 3. That's the answer to the question, but in my class, I don't just want an answer, I want to know why. So if you're telling me it's discontinuous at the point, you need to tell me why it's discontinuous at that point. So let's look at x equals negative 1. Let me rewrite that so it's more clear. When x equals negative 1, we're looking at the red one right there. Why is it discontinuous? Well, we have to run through the gamut. Does the function exist? Yep, the function does exist. It's y equals 2, right? Does the limit exist? Notice from the left and the right, I'm approaching the same y value. That y value is negative 2. So the function exists, the limit exists. What's the issue? They're not the same thing. So how would I write that? I would say the function value at negative 1, f of negative 1, is not equal to the limit as x approaches negative 1 of the function. So they both exist, they're just not the same thing. Okay? Let's look at the next one at x equals 1. Why is the function discontinuous at x equals 1? Again, that's the blue one that I highlighted on there. Why would it be discontinuous? Well, the first thing we always check is, does the function exist? Notice that function is an open circle here, not defined anywhere else. So the function doesn't even exist at that point. So that's simple enough. We just say f of 1 does not exist. Okay. Let's look at the last one here at x equals 3. At x equals 3, why is the function discontinuous? Is the function defined? Well, it is. We do have a solid circle here, so the function is defined here. The next thing we have to do is check if the limit exists. We'll notice as I come from the left, I have a y value of 0. As I come from the right, I have a y value of 2. So the limit from the left is not equal to the limit from the right. If the limit from the left is not equal to the limit from the right, then the limit at that point does not exist. So we know that the limit as x approaches 3 of my function does not exist. And if the limit doesn't exist, then the function is discontinuous at that point. So there it is. Not only did we identify the points of discontinuity, but we specifically stated according to the definition why it is discontinuous at that point. Again, the only three things that we could have written there for justification is the function doesn't exist, like in this example. We could have that the limit doesn't exist, like in this example. Or that we can have they both exist, but they're not the same thing, like in this example right here. So this is a wonderful graph that gives us all three different possibilities. Let's try one more example together. It says the function h is graphed below. At what numbers in the interval -4 to 4 is h discontinuous? So again, we're looking for holes, we're looking for jumps, we're looking for asymptotes. So as I look through this graph, where would I have to lift my pencil? I'd have to lift my pencil right here. If I was graphing right here and right here, I'd have to lift my pencil right here as well. So any holes, vertical asymptotes, jumps, etc. Here's the first one that I noticed was when x equals 2. And then I notice I also have an issue right here when x equals 1, because that's my vertical asymptote. So the answer is really easy. It's -2 and 1. When x equals -2, it's discontinuous. And when x equals 1, it's discontinuous. But we do have to justify why is it discontinuous at that point using the definition. We have to show this work or we're not going to get credit. So at x equals -2, what does it violate? First, we check to see if the function exists. Here's the closed circle. The function does exist. Next, we check, does the limit exist? Well, as I come from the left, it looks like my y value is -1. As I come from the right, it looks like my y value is -3. So notice that left and that right, they don't agree. They're not the same thing. And if the left and the right don't agree, then the limit does not exist at that point. If the limit doesn't exist at that point, the function's discontinuous at that point. So why is it discontinuous? It's discontinuous because the limit as x approaches -2 of my function does not exist. The left side didn't equal the right side. Okay, so that was the red one. Now let's do the last one right here. We need to say why is it discontinuous at x equals 1. Notice x equals 1 is a vertical asymptote. We can do multiple reasons here on this one. Notice this is a vertical asymptote. There is no solid dot anywhere. So that could be the reason right there. You could simply say that f of 1 doesn't exist. That's enough. Right there, because the function's undefined at that point, we know that technically this is discontinuous at that point. But you could have also said the limit doesn't exist, because remember, for the limit to exist, the left and the right-hand side have to be the same thing. Both of these are approaching infinity, but it also has to be a number. And infinity isn't a number, it's more of a concept. It's a never-ending number. It's not one single number, right? So you could have also said, or the limit as x approaches 1 of the function does not exist. Okay? It doesn't matter which one of these two things you cited. You could say the function doesn't exist at the point, or you could say that the limit doesn't exist at the point because it goes up to infinity. Either one of these would have been justification. You did not need to put both of them. Either one of them would have worked for justification. Okay? So there it is. Again, find the points of discontinuities, those holes, the skips, the jumps, the vertical asymptotes. Tell me why it is discontinuous at that point. Don't just give me the answer. Tell me why that is the answer. I hope that helps.